Okay, so hello everyone, and good morning. I hope you can listen me. Please, someone. We will wait a little bit to Sylvia. First of all, I will start on saying thank you to Sylvia, Bodo and Jürgen Garge for organizing this interesting course about the basics of lithium-ion batteries in the framework of SENSIBAT project. My name is Iñigo Gandiaga, and I am the coordinator of SENSIBAT project, and I work from Ikerland in the characterization of modeling of lithium-ion batteries. Good morning, Sylvia.
Good morning. Sorry, but I didn't get access to both the camera and the microphone. So
No
thank you very much. You already started, so I give you the floor. Thank you very much.
Okay.
Sorry.
Okay. No worries. Okay, so today, as you know, is the second day of the zeroing course. And today we will talk about first about the sensors and then about the battery states before a very short coffee break. And after this, we will see how to build a battery model. And finally, we will talk about the implementation of models in a battery management system. Of course, I won't be the one who presents all these parts. I will just present some of them, and then we'll have the participation of Fraunhofer, I think Politecnico di Torino, and Flanders Make. Before starting today's lecture, I will give you a short introduction about the SENSIBAT project. The overall objective, for example, here we have different challenges in today's batteries, and taking as example the automotive market, we can see that more and more manufacturers are introducing battery electric vehicles to the market. These manufacturers are expected to offer lithium-ion energy solutions as their vehicle's primary power source. However, the use of lithium-ion batteries also comes with safety risks, while safety is one of the most important aspects for an electric vehicle manufacturer, because a single incident could turn the public against this kind of vehicles. Lithium-ion batteries are also sensitive to fast charging and high voltage operations. In current electric vehicles, the lack of understanding or information from the cell and the conservative and large safety margins limit the use of the available battery capacity to approximately 90 or 80% of the installed one. In addition, the capability to measure in real-time internal battery cell key parameters would greatly help to understand the underlying processes and make the use of lithium-ion battery safer while using the full battery capacity, that's to say 100% of the installed battery capacity. So more accurate and real-time feedback of the cell and battery states allows the use of a smaller safety margin during, for example, fast charging, which can be translated into users' preference like shorter charging times, more power, and longer range. And our idea is to overcome all this with internal sensing systems. Finally, accurate sensing of internal parameters also leads to improved insight in the battery condition and its usage history, and this will allow for a more accurate energy management control loops that will maximize the battery lifetime and allow also for a better and safer second life usage. The overall objective of SENSIBAT project is to develop sensing technology that measures in real time the internal battery cell temperature, pressure, conductivity, and the impedance of different parts of cell parts. For example, the anode, cathode, and electrolyte of the lithium-ion batteries. The data from these new sensing technologies and gained insights into the possible degradation and failure mechanism will be used for the development of improved state estimator functions to be included in the BMS. And to achieve these overall objectives, the main objective has been broken down into 5 sub-objectives that you can see here. The first is to develop a smart battery cell sensor technology. We are going to develop in the project 2 kinds of different sensors. On one hand, 2-dimension matrix capable of sensing the spatial temperature and pressure inside the battery cell. And on the other hand, an internal sensing auxiliary electrode printed on the separator and placed, of course, inside the battery cell. And this electrode will allow to perform in situ electrochemical impedance spectroscopy test. The second objective is to integrate these 2 sensors in battery cells. We will do it separately. In 5 ampere-hour cells, we will have pressure, temperatures, sensor matrix, and in 1 ampere-hour cells, we will have the third electrode sensor. And the overall objective, of course, is to prove that the integrated sensor do not influence the cell electrochemical behavior, and then also to get more knowledge from the cell. The cells with integrated sensors will be used for a third sub-objective, which is the development of a 24-volt battery model with level 1 or pressure and temperature sensor integrated. And here we will have also a slave PMS, which will have a multi-cell monitoring IC and a master BMS to connect the slave BMS to it and to have inside it programmed the battery state and the novel battery state algorithms, which are the core of the fourth sub-objective. Finally, we'll have also an analysis of the cost of the system and also a recyclability study. Last but not least, I want to mention that all deliverables of the project are public and can be found on the SENSIBAT project website. Now we will start with the first part of today's lecture. I will talk about the different existing sensors to measure battery state in general, and then Michael Young from Fraunhofer will give an introduction to the developments related to the temperature and pressure sensors in SENSIBAT project. In my talk, I will give you a brief introduction to Ikerlan, my company, and after this, I will explain the different 16 sensors for batteries. Ikerlan is a technology research center located in the Basque Country with 2 different locations, and I belong to the energy storage area, which is located in San Sebastian in the north of Spain. And we are an open and dynamic company at the service of industrial companies. We belong to Mondragon Corporation, which is a corporation of worker cooperatives, and it is the seventh largest Spanish company in terms of asset turnover and the leading business group in the Basque Country region. In addition, Ikerlan is part of the Basque Research and Technology Alliance, where more than 3,700 researchers collaborate in different research areas. Nowadays, we are around 360 people divided in 3 research areas at Ikerlan, and I belong to the energy and power electronics unit, where we form a team of around 80 researchers. In the energy and energy storage and management area, we cover a wide range of the energy storage value chain, starting from the technology selection and characterization, and following with the control system design, and finally with the development of the battery system itself. Regarding the battery sensors, I want to start the lecture asking which is the objective of a battery sensor. The battery sensor is an important part of the battery research and a must for its industrial application, as the sensor informs about the exact battery status. The most common measures are the battery temperature, together with the voltage and current, but in recent years, new battery sensors are arising with the objective of having a deeper knowledge about batteries. And as I mentioned before, today I will explain the somehow called basic sensors, and then Michael will explain more in detail the more sophisticated ones. I will start with the electrical sensors, and here the first sensor that we have is the voltage sensor. Voltage sensor is a sensor used to calculate and monitor the amount of voltage in an object, of course, in this case, a battery. In voltage sensors, the measurement is based on a voltage divider, and 2 main types of voltage sensors are available. Capacitive type voltage sensor and resistive type voltage sensor. In lithium-ion batteries, the voltage can be used as example for a state of charge calculation, state of health also, or power. Although its relation will vary in function of the chemistry and state of the battery. Here you can see how different the chemistry voltage changes at different state of charges, for example. It can be also used for cell balancing, and in some cases it's also used for aging analysis under deeper analysis of voltage changes during different processes of the battery. And finally, maybe one of the most important usage of the battery voltage sensor in lithium-ion batteries is to supervise that the battery is working in the safety operation area, which is around 1.5 or 2 volts up to 4 or 4 maximum 4.5 volts. Then continuing with the electrical sensors, we have the current sensor or ammeter. And ammeter is a measuring device that is used to measure the flow of electricity in the form of current in a circuit. The most used current sensor in the battery industry are the shunt resistor and the Hall effect current sensor. And as we said before, battery current sensor measures the charge and discharge current flowing through the battery, and are critical for maintaining a healthy battery, and also as the voltage are critical for maintaining a healthy battery, as the voltage sensor will detect, with the current sensor will detect if it is working in the safety operation area of the cell. and current sensor are also useful tool to estimate different battery states and in this case, for example, the state of charge. Linked to the current sensor, we have the ampere hour meter, which registers the integral with respect to time of the current of a circuit in which is connected. So we can say that ampere hour meters are used to measure the quantity of charge that the battery or cell has been charged or is discharged. Then, following with the electrical sensors, we have the electrochemical impedance spectroscopy meter, which measures the impedance of the battery at different current frequencies to provide data on the battery condition. This is not as common as the previous two sensors, but it's very used for diagnosis or analysis of the aging processes of the battery, for example. This makes the impedance spectroscopy an indispensable device, for example, for optimizing component materials in research laboratories. EIS is particularly sensitive to systems that contain several impedance elements, which makes it well suited to study a multi-component device such as a battery, because different components and processes within a cell operate on different time scales. That's to say, they have different time constant and can be separated in the frequency domain by using the EIS. This AC current is usually applied at cell terminals, as you can see here. But for example, in the SENSIBAT project, we will introduce a third electrode inside the cell to allow in situ electrochemical impedance spectroscopy test in order to enhance the knowledge about the behavior of different parts of the battery. Linked to the EIS meter, we also have the AC internal resistance meter, which usually measures the internal resistance of the battery at 1 kilohertz, and it's commonly used as a quality control check in the battery production or battery pack assembly industry. Now we switch to temperature sensors. This is again must in the battery research and also must in the battery applications. The most common temperature sensors are the thermocouples, RTD or resistance temperature detector, and thermistors. In this case, the temperature sensors are mainly used to verify that the cells are working in the safe operation area. A thermocouple is composed of two different metals joined at one end, and when the junction of the two metals is heated, a voltage is produced which is proportional to the temperature. Thermocouples are used to measure the temperature of cells, for example, in the labs, and also to measure the temperature of cells, maybe not all cells, but some of them inside a battery pack. RTD sensors take advantage of the effect that temperature has on the conduction of electrons, so that with an increase in temperature, there is a change in the electrical resistance they present. And usually they are made of copper, nickel, or platinum alloys. They present different behaviors in function of the temperature. Finally, we have the thermistor, which is a temperature sensing element composed of sintered semiconductor material that exhibits a large change in resistance in proportion to a small change in temperature, as you can see in this graph. Unlike RTD, we change resistance in a almost linearly form. Both the negative coefficient transistor and the positive coefficient transistor exhibit a distinct nonlinear change in resistance. For example, in this case, a negative coefficient transistor actually decreases its resistance while the temperature increases. The use of a transistor is very common in battery packs, as a small change in temperature translates into large changes in sorry, in resistance. Then, following with temperature sensors, we have other kind of sensors that are maybe more used in labs. For example, the thermography, which is a technique for determining temperature at a distance and without the need for physical contact with the objective to be studied. It captures the infrared radiation of the electromagnetic spectrum using thermal cameras or thermovision cameras, and can be used to detect which part of a battery cell or a battery pack get the hottest during use. Then we have the heat flux sensors. They measure energy flux onto or through a surface. Convective and conductive heat flux is measured by letting this heat flow through the sensor, and radiative flux is measured using heat flux sensors with black absorbers. The absorbers covers radiative to conductive energy, and a heat flow sensor can be used in combination with a surface temperature sensor to obtain to estimate the internal temperature of a battery, for example. Then we have the fiber Bragg grating, which is a type of optical fiber that reflects particular wavelengths or light and transmits all others which can be used to measure temperature. Embedded fiber Bragg grating sensor within lithium-ion, for example, battery pod cells, can be used to monitor the internal electrode strain and temperature during cycling. Then the last sensor that we are going to analyze are the pressure sensors. And as you may know, the act of charging and discharging a lithium-ion battery produces changes in the temperature and electrochemistry of the battery, but also in the mechanics of its internal components. And these dynamics cause changes in interface pressure within the battery housing, and we colloquially say that these changes in pressure give the effect of a battery breathing. Over time, this breathing can affect the battery performance, and in extreme cases can lead to potentially dangerous reactions. Recently, battery designers have begun using piezoresistive force and pressure sensors, the technology to analyze the effects of charging and discharging lithium-ion batteries in long-term life cycle tests. And this same type of sensors can also be embedded within the actual device to help the alerts and to help to alert the end user of potential battery failures at cell or maybe more at module and battery pack level. Regarding the sensor technology, on one hand, we have the pressure transducer, often called a pressure transmitter, and it's a transducer that converts pressure into an analog electrical signal. On the other hand, the load cell is a force transducer that converts force such as tension, compression, into an electrical signal that can be also measured. And finally, we have the strain gauge, which is a type of electrical sensor that can be attached to a battery cell, and its primary use is to measure force or strain. The resistance of this sensor when the force is applied it changes its resistance, and this change will give a different, of course, electrical output, which can be measured, and it will inform us about the pressure, force, or tension that it's suffering. Apart from SENSIBAT project, I would like to mention other projects that use non-common sensors. For example, in Spartacus project, they are using mechanical and acoustic sensors together with other kind of sensors to achieve similar goals as the ones in SENSIBAT project. And in InstaBat project, they are using optical fibers with fiber Bragg rating and luminescence proofs, and also reference electrodes and photoacoustic gas sensors to measure battery states. Of course, all these sensors are always in combination with the so-called common voltage, current, and temperature sensors. So as a summary, we saw that there are a lot of different kind of sensors for in situ battery measurements, and today we analyze in more detail 3 of them. The electrical sensors, as the voltage and current sensors, together with other more sophisticated ones. Then the temperature sensors that are available in different types and resolutions in function of its final application. And finally, the pressure sensors, which are going to be more in depth explained by my colleague Michael Young from Fraunhofer in the following talk. So please, Michael.
Thank you. So, hello, good morning and welcome to my presentation. I want to thank Inigo for the very good introduction into the field of sensing applications in batteries. This is a point where I can directly dive in and present you the representation of sensors and the things that we do in SENSIBAT project for integrations of thin film sensors, especially into the battery cells. I will start with a short introduction on our institute and my working group. Afterwards, I will define and discuss about the requirements that we face and we have to fulfill for integrating sensors inside the battery cell. After this, I will focus on the basics of thin film technologies and the respective sensors that can be derived from these technologies for temperature and pressure sensing. And I will then end with some remarks on specific solutions that we introduced for the SENSIBAT project to fulfill all the requirements of the integration of sensors into the battery cells. Yeah, let me start first with a glimpse on our institute. The Fraunhofer Institute for Integrated Systems and Device Technology is one of over 70 Fraunhofer institutes that are located all around Germany and also some of them abroad. And our institute is located in a town called Erlangen, which is roughly 200 kilometers north of Munich. And Erlangen has this third largest university in Bavaria. And this has roughly 30,000 students. And the Fraunhofer Institute is closely located on the campus of the University of Erlangen that holds all the technical disciplines. And let's say the location also points out the close cooperation with this university. In fact, the head of the institute is also a professor at the university. And there are joint labs that are used between both institutions. For example, here you can see our large cleanroom facility, which can be accessed from both the university building and also the Fraunhofer Institute's building. And this points out the close collaboration. Typically, we have around 300 members of staff. And these are, let's say, accompanied by 200 roughly students, internees, and so on. This also points out how closely we are interacting with the university. So our institute is aligned along the value chain of power electronics. So starting from materials development, prototype fabrication of semiconductor devices and thin film devices like I will present, then our activity is located in the Department of Hybrid Integration that includes this electronics technologies I will present later, but also things like assembly and interconnect technologies for power electronic devices. And then it is rounded up by two application-oriented departments that are dealing with vehicle electronics, not only cars, but also trains and aeroplanes, and intelligent energy systems. And within SENSIBAT, there's a cooperation also inside our institute between two groups. So our group located here in the electrical components technologies, and a group located in the intelligent energy systems department that is active in the battery management system development. And they are integrating our sensors then into their application. So our group is mainly active in the development of material systems, deposition steps, functionalization of materials, and also aging of materials, like, for example, corrosion investigations. And on the other side, the application of these materials, integration of materials into layer stacks, the development of devices, and then the connection of these devices into systems and addressing the applications. So this centers around topics like nanomaterials research. You see an example here where we look inside a liquid through a translucent electron microscope, and we can directly observe the etching of a tiny particle by a highly reactive gas bubble that is formated inside this liquid. Therefore, we supply microelectromechanical systems that can fulfill this task. Then one point is the flexible thin film electronics. This is also the field that is stressed inside the SENSIBAT system. We are running a thin film technology, which is known from, for example, when you look at the display in front of you. This is run by thin film transistors that control the light intensity at each pixel. that gives you the appearance of the pictures that I show here. And we're into developing such transistors and transistor circuits. For example, these here are pixel electronics for a transparent display. We are developing this in flexible shapes and transparent. We do simulations, and we also integrate this with different light sources to yield the final display applications. Then we're in the field of sensing technologies. That's also the reason why we joined the SENSIBAT project. One of them is electrochemical sensors, where we can analyze liquid for certain ion species. We have a range of materials that can be analyzed, and the signal and the concentration of this analyte is directly converted into an electrical signal. So we get an increase of 60 millivolts per decade of concentration change. And this can then be easily integrated into electronic applications and easily read out by electron devices and used for further evaluation, for comparison. For example, in the agricultural field, this can be correlated to meteorological data and can then give a guideline for proper fertilization of the field. Yeah? And of course, what is contributed to SENSIBAT are the physical sensors. So we already had an earlier project on the integration of temperature sensors into battery stacks. In this case, the battery sensors were located in between the battery cells, but developments went further. We miniaturized these sensing elements, and now we're able to integrate them also into the battery cells. I will come back on this later. And we can also integrate them in a matrix style so that we can read out temperature distributions over spatial arrangements. And this is the task that we are fulfilling in SENSIBAT. Yeah, this brings me to the requirements that the integration of such sensors. No, my system is somehow stuck, sorry. I hope I'm still online. Can you hear me?
Yes, we can.
Yes,
we can hear.
we can hear you well.
But unfortunately, my PowerPoint is not going forward. I just received a send clock, so I don't know what the problem is at the moment. So if
share it again, maybe refresh.
If this persists,
Now it works.
I have to go out. I think now it went on. Yeah?
Yes,
sorry,
works.
sorry for this short interruption. Yeah, so when we want to integrate the sensors into the battery cell, yeah. So yesterday there was a question after Professor Garch's presentation, where one of you was asking, we can only measure the skin of the battery cell, but what is necessary to bring this temperature measurement inside this battery cell? And for this task, we have to consider let's say the work plan from two perspectives. One perspective is that by bringing in the sensing elements, the cell operation must not be changed. Yeah. So this means the sensor must have, let's say, somehow negligible form factor. It must not be too thick. It must not add any edges, which might be a harm to the pouch, for example, or to the electrodes that are integrated inside. It must not add additional volume, so the battery pack has to stay in a compact shape. Yeah, it should not be extended by this additional sensing element. In addition, we have to get the measurement signals out. Yeah, as you have seen from Inigo's talk, these sensing elements are really bulky devices. Yeah, let's say the form factor of let's say an IC, for example. Yeah, which is several hundreds of micron in thickness, or if not millimeters. And also the lateral dimensions are in the range of several millimeters. This would add an additional impact to the battery cell. Yeah? And also, even if we overcome all these things like any edges or additional volumes, we have to guarantee that the chemical balance inside this battery cell is not altered. So there should be some kind of inertness of all the materials that are in contact to the electrolyte, for example. And we have to take measures against all problems that might arise from these materials that are brought into the battery cell. On the other side, we can have a look at it from the other direction also. So the sensor itself must withstand the electrolyte interference. So if the electrolyte would, for example, dissolve the encapsulation or the sensing materials, this would make the sensor vanish within a very short time, because the electrolyte typically is very aggressive, as we have already experienced by Professor Garke's nice talk yesterday around noontime. Yeah, and also we have to guarantee that the physical quantity, let's say the measurement signal, can be transduced through the encapsulation and out of the battery cell without any losses. There should be no, let's say, resistive loss, no capacitive loss, no parasitics coming with that. And we analyzed these requirements, and we found that the thin film technologies meet these requirements very well. For example, they offer flexibility. They offer a very thin appearance, so we only use several micrometers for defining such an application, or let's say tens of micrometers, which is very thin with respect to the overall thickness of the battery cell. And by this, we can also define feed-throughs that can be led through the battery sealing, and can make a connection to the outside and to the battery management, where the sensor data are then handled for further knowledge gain. Yeah, what typically is such a thin film system? Yeah, there are several expressions around that are used for description of these material systems. Typically, this come with attributes like thin, flexible, large area substrates. There's also this Tolay expression in the word that means thin, organic, and large area electronics. This is very common to use. Typically, this integrates electronics and sensing functionalities on one sheet of flexible substrate. This can, for example, hold for distributed sensing capabilities. The local readout of these sensors, signal conditioning, amplification, for example, and handling, which means also multiplexing of these signals to the outer world. This can be integrated onto the sensor sheet, depending on the complexity that is allowed for the specific application. I will come back to this later. So if we drive it to an, let's say, very vastly developed appearance, then there could also be things like communication functionalities integrated onto this sheet. For example, we are also into the development of RF type thin film transistors that can be used for driving such an antenna like it's depicted here. But this is another thing I don't want to comment on today. Yeah, the goal is to deliver additional functionalities for existing applications and also for the enabling of novel applications that have not been yielded before by traditional technologies. And the second point is also that we want to guarantee a very simple system assembly. Now, this is clearly the case if we can go for some wireless communication here, but also a lot of, let's say, hardwired readout schemes exist where we can then attach, for example, ICs or SMD components to the surface of these layers to integrate the novel thin film electronics with conventional electronic building blocks. Yeah, what are typical thin film technologies? So you know a lot of these maybe from photovoltaic technologies, also from the processing of battery cells. Yeah, there's a lot of let's say coating, doctor plating. This is typical wet processing technologies. However, the majority of thin film technologies are typically based on vacuum processing. Yeah, you can see here a picture of a typical chemical vapor deposition process where we have some precursor molecules that are adsorbed on a surface. Then they react, they get dissociated. In this case, for example, typical carrier molecules, for example, for aluminum oxide deposition are trimethyl aluminum molecules that have an aluminum atom that is stabilized by 3 methyl groups, and then upon adsorption to the surface and, let's say, receiving some extra heat from the surface, these methyl groups can be ripped off and can, let's say, can join with some free hydrogen electrons to make up methane, and then can be carried away. And the aluminum is left on the surface, can, upon some temperature influence, also move on the surface to some extent and can form a closed aluminum film that can then afterwards be accompanied by additional oxygen atoms to give a very good insulator that is also used in our application. So besides this chemical vapor deposition, that is, for example, also used for the deposition of silicon for thin film solar cells. Yeah, there's a lot of physical vapor deposition techniques. One of the most common is the evaporation of materials that are then condensing on the surface and form, for example, metal films. This is very commonly used. And there's a range of technologies that can also be used for the definition of insulating materials, of semiconducting materials. For example, we use for our thin film transistors indium gallium zinc oxide compositions or mixed oxide material that gives good semiconducting properties for further realization of these thin film transistors. So there's a broad range of materials available also from traditional integration technologies like silicon technology or 3-5 semiconductor technologies that can be applied to give new applications and also, for example, the sensing applications that we are discussing about here. Typically, with these materials, you're not able to do a direct patterning of the material. So you rather have to go for, let's say, this 4-step processing, starting with layer deposition, then putting on top a light sensitive photoresist material. This is then exposed by a certain light pattern and can be developed to give a mask that can be used for etching process, where this initially deposited layer is then structured. And after structuring and cleaning, rinsing of the surface, the resist is removed, and then you can have, let's say, an integrated cycle of feature definition that is repeated for several times, for example, up to 25 times in silicon processing. And this is the typical, the typical approach of so-called subtractive patterning. Now, this is a very elaborate scheme of providing features that can be used for electronic applications later, but vice versa, it defines and gives highly precise elements and can be scaled down to several nanometers of size fidelity. So this is ideally suited for prototyping, for lab instrumentation, where it is about very high resolution and high validity of measurement results, and is vastly seen in testing systems. When it comes to a mass production of such devices, there's also the need for, let's say, some kind of cost awareness, for example. And for this stage, people tend to go more to so-called printing technologies, which offer an additive manufacturing, meaning that the material is from an initial stage only deposited at a position where you want to have it. So the features are directly formed during those printing processes. This also comes with the ability to have a roll-to-roll integration, so to produce a large number of such devices in a very short time. On the other side, there's always the question if there's a good availability and maturity of the materials that are used. For example, it's not so easy to realize good homogeneity of the materials properties on each scale of processing on the web width of these foils that are here in this case run in or fed into a drying oven, for example. And you always have to decide at a distinct point where's the point where it can go from this traditional vacuum technologies to printing technologies to serve for the needs of large volume applications. An example that is shown here is for screen printing, where you have a mesh that is open at certain points where you want the so-called paste to be deposited. And upon, let's say, doctor blading this paste through this mesh, you can yield the features on your substrate, and this can then make up the functional building blocks of your application later. Yeah, these are the basic thin film technologies. When we then go into closer contact to the application, we also have to decide how the connection to the real world is made. And there are some, let's say, trade-offs between what can be integrated in this thin film electronics, what has to be done by conventional electronics, and therefore we define two, let's say, domains. Yeah, sorry. One is the monolithic domain, meaning everything that can be processed in this thin film technologies, as it's seen here. We have the resistors that are, for example, temperature sensitive in this case, integrated with all the wirings and all the transistors needed for readout. And the opposite way, the opposite domain is hybrid integration, meaning to, for example, solder or to glue anything we can think of in addition to the surface of this thin film applications. This was the thing that is very fastly evolving at the moment. There are a lot of techniques developed that can offer the hybrid integration of conventional, of discrete devices onto thin film, so-called backplanes. And this is a very, very fastly evolving and emerging field. And we're also studying an application or an activity in this field for future functional and building block integration that can give us new capabilities for future systems. So far, my introduction on the thin film technology. I will come back to a thing that already was introduced by Inigo in the last talk in a very well manner. This was the different possibilities for sensing of temperature and pressure inside the battery cells or in the battery system. In this presentation, everything is about the thin film electronics, and I will comment on these temperature and pressure sensors solely from the point of view of the integration into the battery cell in these requirements that I already defined, meaning it must be thin, it must have no topology, it must be integratable, and also give certain resistance against everything that's happening inside the battery cell. So the first instance of these temperature sensors already mentioned by Inigo is the thermocouple. He already mentioned that you need a combination of two metals that make up a certain, let's say, barrier voltage at their contact point, which is shown here on the right side, on the left side, sorry. This is a combination of a nickel film and a copper film. Yeah. And upon heating this point, this work function difference at this contact point can be transferred to the outside. So it has to be clearly stated that there are a lot of requirements to be fulfilled to get a proper measure of this voltage that is here available on the inside. For example, the two connection points to the outside must be on the same temperature level. So there must be no, there doesn't have to be any deviation between the temperatures at these 2 points. Otherwise, the work function differences here would add up and would give a distortion on the signal that you find here. Also, it must be a well-defined contacting scheme to the outside. And this is a thing that has to be watched at with very carefully, because it not only is about this thermocouple contact points, which are often welded in technical applications, but can also be realized by simply putting one metal on the other by a thin film technology. However, the readout is very difficult, and also has to guarantee that this voltage not breaks down. So you have to read it out at a very high impedance with a certain amplifier that is needed in the outer side, in the outer world. And this is a thing that has to be tailored very carefully. Another possibility, is the use of a Schottky barrier. Typically, this is made up of a semiconductor, which is in this case contacted by a material that is very well matching with respect to the work function of the semiconductor. For example, aluminum that makes a good contact on the one side. On the other side, there's a material that has a strongly differing work function, and this will make up a rectifying contact here. And you can analyze this rectifying contact, especially the turn-on voltage of this Schottky diode that is evolving here. And by analyzing this with respect to the temperature, you can then derive the temperature that is active at this point. This again is, let's say, an integration scheme that makes use of a lot of dedicated materials that have to be controlled in a very good manner. And the bill of materials is steadily increasing as more as materials you integrate into your application. So you have to carefully think about if you want to integrate additional materials to have this readout capability from a rectifying device here. And if you can afford to integrate this, more or less costly materials also into your application. Then, as a third alternative, we have this resistive temperature device that was already introduced by Inigo as a RTD device. This is typically an instance of, for example, a metal that is very sensitive to temperature. Typically, the change is around 0.1% per Kelvin. And this is then read out, this temperature change. And okay, the better the reader is, the better, the larger the temperature rise is. But you can also resolve temperatures below a resolution of 1 Kelvin with such a technology. There's a range of alternative materials. For example, in this first instance, we investigated into a few years ago, which was purely printed. There we used a polymeric material that was filled by conductive particles, and upon heating, the polymer expanded and particles successively lost contact, so that the resistivity was steadily increasing upon heating of the material. However, as the basic principle of this application is a mechanical expansion and then also shrinking again, this has some latency and also is prone to some hysteresis effects and some, let's say, aging that cannot be neglected. We did not follow this way, or do not follow this way nowadays anymore. But we focus more on this resistive temperature devices that are also applied in the SENSIBAT project, as I will talk about later on. Yeah, next question of the research, especially for SENSIBAT, is the pressure sensing. And typically, as already shown by Inigo, by this pressure cell approach, people use a membrane or coming with a cavity. And there are two possibilities to read out the deformation of this thin membrane upon applying forces to it. This is on one side, if the membrane acts as an electrode, you can use this gap here as a parallel plate capacitor. And upon deformation of this membrane from the top, the thickness between the two electrodes is reduced and the capacitance increases. This is one of the possible readout mechanisms. The other is that you directly use a piezoelectric effect or piezoresistive effect, meaning that if you have, for example, polysilicon as material here, this will change its resistivity upon deformation. And the resistivity change can also be used to analyze the grade of deformation. And by this, with all the mechanical parameters, you can then calculate the force that is applied to the membrane. And this can be, let's say, reasoned by some change of air pressure, for example, or by some mechanical impingement from outside. This is a very well-established approach, which is frequently used in silicon microelectromechanical systems that are processed in a very cheap and a very, let's say, large volume way. And if you buy, for example, pressure sensors at an electronics distributor, that in most cases it will be one of this type. However, it needs for a rigid substrate. It needs for a rigid frame around this membrane. And this is a thing that is clearly not feasible for the required flexible substrates that we want to apply for integration in the battery cells. So there has been one, let's say, derivation of this approach by adding an insulator inside this cavity that is deformable. Yeah, for example, a polymer, in some cases, a polymer that is also filled by additional conductive particles to improve the sensitivity. And this has somehow the same principle behind. So upon applying a force to this structure, you can have a deformation, you can bring two electrodes closer to each other, and by this change the overall capacity. So to complete the picture, especially with a view on thin film sensors, I also will use a few words on the piezoelectric and piezoresistive materials. The piezoelectric material typically reacts with a voltage signal if also such a parallel plate configuration is submitted to forces, and the voltage that is coming out of this stack is related to the force. Yeah, it's a more or less linear behavior in the range of interest, can be designed for typical applications. Again, here we have the requirement of a high impedance readout, so the potential difference will not break down fastly. But as you see here, this can be nicely integrated also in this thin film style, as well as it holds for the piezoresistive materials that I already mentioned for this membrane readout. This is a principle where upon applying a force, you get a change of the electronic structure inside this material, and you can detect a resistivity change and can read out this resistivity change by a simple current or voltage measurement. Yeah? These are very well-known principles, also available as some products. On the other side, also a principle that need for integration of additional materials. You need the piezo active material, you need certain electrodes that make good contacts without any charge states at the interfaces and so on. So this is also, let's say, an exercise that is very elaborate, and one must think if it is appropriate to go for such an integration for the specific application. So one thing I want to add at this point is how to read out sensors in a matrix. So typically, if you have a range of 6 or 9 sensing elements, you have different possibilities to read out these elements. So you can have the most simple way, just to add 2 wires to each of the elements, so you can get full access to each individual element without any interferences between the elements. However, this causes a lot of wirings that have to be, for example, fed through the ceiling of your battery cell. So you can think of, and there's this is already established, different ways of reducing the number of wires. For example, when we go from this instance A to B here, we can add, for example, a common ground contact to all of these elements. So we can read every element at its certain line with respect to this common ground connector. And this reduces dramatically from, let's say, if we refer to 9 elements, from 18 wires here to only 10 wires. Huh? If we go one step further, we can not only connect the rows in parallel, but also connect the columns in parallel. This gives a so-called cross-point matrix, and this reduces the number of wires in a further step dramatically. However, we always have to be aware of the large effect of the parallel circuitry that is arising, because if we're contacting one device, there's possible paths that are in parallel to this element, like shown by the red dotted line or dashed line here. And this is only one path. There are numerous others. So this can be worked around to some extent by adding rectifying elements in series, because then these paths are somehow blocked at certain points. We can also, like it's done by in the displays, apply some kind of row scanning, which needs for additional switching elements that are activating one row after the other. And this is also the principle that we follow in SENSIBAT for one of these sensing arrays, is to rule the influence of the single devices out by multiple measurements. And this clearly is, let's say, the most simple way for device fabrication and for feeding out the wirings, but on the other side has a lot of effort on the data handling side. Yeah, with this, I will come to a more specific view on these sensors that are integrated and are developed under SENSIBAT. So first of all, we have a range of resistive temperature sensors that are in principle arranged like it's shown here. We have a sensing resistor, which is made up of a meander of a metal line, which is, let's say, a serpentine that gives a long length and a small width, which yields in the end a high resistivity. And the aim of this exercise is that the resistivity of this sensing element is dominating the overall resistivity, which is made up of the sensing element's resistivity plus the conducting wirings that are leading to this element and back. Yeah? And what we did in SENSIBAT is we assessed a lot of materials for integration in such an application. And here you see some measurement curves for a platinum-based sensor. You see that they're very nicely linear, have a nice behavior that can also be used for, let's say, a high resolution readout of this temperature at special sites. However, we have some inhomogeneities between different sensing elements that are neighboring. And this is a thing that is typically ruled out in, say, typical silicon technologies or in resistive sensor arrays that you can buy from a vendor by things like laser trimming, for example. And this is a technique that is not applied in SENSIBAT, but in SENSIBAT we want to focus on an initial analysis of these sensing elements, and later on then the readout and the direct and exact determination of the resistivity of the single elements by this data handling algorithms. The next point is the pressure sensors. I already introduced that principle where we have this elastomeric material between two metal electrodes, and that can be submitted to force and then be compressed. This typically follows the normal formula for the parallel plate capacitor, which defines the capacity as the permittivities times the area divided by the thickness. And if we reduce the thickness, the capacity will increase. And this is shown here in this picture. We applied in this case a polyurethane material, and then we applied pressures of 100 kilopascal, 200 kilopascal, and you clearly can see that the capacitance of the overall system is reacting on applying this force, and can then, or by this, be utilized for reading out the forces and the pressure that are that are active inside this battery cell. Yeah, with this, I will come to some basic principles of the processing that is applied in SENSIBAT. So typically we process the sensor matrices on a substrate, on a flexible substrate that is processed by spin coating it onto a rigid carrier. And with dedicated heating cycles, we can stabilize this material, and this can be submitted to processing temperatures as high as 350 degrees Celsius that are largely extending the range of temperatures that we need for deposition of this chemically deposited materials. So we can run the whole processing scheme also for our transistor circuits on this. And afterwards, we can then detach this flexible material from the rigid carrier again and make this flexible application accessible. You can see this here. These are the 1 ampere hour sensor matrices that have been then by laser cut out of the rigid carrier and can then be utilized for further integration. And what is important for an integration is, as I already mentioned in the beginning, is a proper encapsulation. And the encapsulation is tested in this case against the electrolyte by dipping it into the electrolyte for several days, up to 1 month. And in the beginning, we found a lot of problems like delamination of this encapsulation from the sensing substrate, like wrinkling, like bubble formation. But in the end, by proper post-deposition treatment, proper, let's say, definition of the surfaces before depositing the encapsulation, we ended up with a very stable encapsulation that can also be submitted to the cell production. And at the moment, there are some tests active where batteries are cycled for a longer number of times. And let's say for the first few cycles, up to 10, 15, this encapsulation has proven its validity and showing that the whole sensor matrix is stable against the environment and also does not have an effect on the operation of the battery cell. Yeah, this brings me to the last slide. So we are halfway through the project at the moment. So this technology was already established. Also, these sensor matrices has been defined and produced in the first version. Mounting with 1 ampere hour cells inside SENSIBAT is underway. Cycling tests have already been starting and will then be reported at the end of this month. At the moment, we're scaling this technology to 5 ampere hour cells, meaning that we go from matrices containing 12 elements to 35 elements. So it's a threefold increase of the complexity. But as we already established this in this level 1 technology, all the, let's say, wiring requirements, the crossing of the lines and so are directly convertible into this 5 ampere hour cell layout. So this should be a transformation that should come without any additional problems. Next is then the electrical system integration of the colleagues who developed the battery management system, who will also do the readout of these elements. And in the end, this will be validated by monitoring inside 5 ampere hour cells during cycling tests. So with this, I come to the end. Thank you for your attention. and all the colleagues of SENSIBAT and the involved colleagues at IISB from other projects who contributed to this technological development. Thank you.
Okay, Michael, thank you. Thank you very much for your presentation, and hello again. Yeah, again, Iñigo Gandiaga, and after seeing the main sensors and variables to be measured in a battery, we will now analyze how they can be used to estimate the battery state indicators, such as the state of charge, state of health, and a state of function or a state of power. The use of these indicators, or the main objective of these indicators, is to ensure a safe operation of the battery without, for example, overcharging or over discharging it. And in addition, it can also help to satisfy the design life of a battery, using it in the best way possible from both perspectives, the battery and application. This is the agenda that I will follow. I will present first a review of the state of the art. Then we will start from the conventional methods to more sophisticated ones, and also I will introduce some disruptive methods. Sorry, because I'm not very familiar with them, but we will try to explain it a little bit. Okay, so first of all, I would like to start with a definition of the state, battery state estimation. Generally speaking, in the battery industry, we will see that there are three main battery state indicators. First, we have the state of charge, which indicates the stored energy in form of a charge in a battery. So this is something similar to a fuel gauge of a combustion vehicle. And in summary, the battery SOC increases while the battery is charging, and decreases while the battery is discharging. Then we have the battery state of health, and is the generic form that we call the battery health. Summarizing, we can say that it indicates the maximum storable charge in the battery. Although in some applications it may take into consideration also the evolution of the internal resistance. Finally, the state of power or function, which calculates the amount of power available for defined time interval given the current power use, temperature, and other conditions. It is also important to mention, as you can see in this figure, that all those metrics are correlated. So we must estimate accurately the state of health if we want to have a precise state of charge value during the whole life of the battery, because as you can see here, we may have some part of the battery that is not more usable when the battery is getting age. Regarding the state of the art, and again, generally speaking, we can divide the battery state methods in four main groups. First, we have the direct measurements, and inside them we have the conventional methods, which are the open circuit voltage measurement and Coulomb counting. Then we have the model-based methods, which are based usually in junction with a electrical model of the battery. In a third group, we have the data-based methods, which are based in artificial intelligence techniques. And finally, the novel or non-common methods linked to previously explained heat flux, strain gauge, and ultrasound sensors. Okay, if we go to the most common methods, we have the Coulomb counting or ampere-hour counting method, and its basics is that integrates the charge or discharge current of the battery to estimate the state of the battery. However, this method is not capable of estimating the initial state of charge of the battery, and it needs also some recalibration, as it is all the time taking into account, also may take into account the error of the current sensor. So it is always or almost always worked in conjunction with other estimation methods such as the open circuit voltage. So Coulomb counting or ampere-hour counting method can be also used for state of health estimation, and it consists of measuring the ampere-hour transferred from or to the battery to calculate the remaining capacity. So it's to say to do the full charge and discharge of the battery. Finally, it's important to mention that there are some enhanced techniques which use the Coulomb counting in combination with the voltage measurements or derivative voltage and derivative capacity measurements to enhance the precision and to minimize the time needed to perform an estimation or to analyze deeper de-aging processes occurring in the cell. This method usually use the ampere-hour counting between two state of charge or two different voltages to estimate, for example, the state of health. So basically, the most common method to estimate state of charge and state of health in the battery is the Coulomb counting plus OCB, which is to measure the voltage and to estimate the charge or the state of charge of a battery, or just to do a complete discharge or a partial discharge to estimate the state of charge and the state of health of the battery. Then we have the impedance spectroscopy technique, and this is again a direct measurement method, but it's a more complicated one. So in this case, the relation between the impedance and state of charge is not as stable as the SOC and OCB relation. And the major problems are linked to the impedance change with the SOC, because it is not always sensitive. You can see that we have in some point that we have almost the same impedance at different SOC values. In addition, the impedance change is more sensitive to temperature change than to the shock change, and then therefore compensation must be addressed if we want to take out of estimation this temperature influence. The impedance also changes a lot depending on the state of health of the battery, and therefore to estimate the SOC we need a compensation, but it can be a good indicator of the state of health of the battery. Finally, as I mentioned before in the sensor presentation, this estimation technique has been usually used at research labs, and in this case to parameterize an electrical model in order to estimate the SOC and SOH estimations states. Sorry. And regarding these models, now we switch to the model-based methods, which are often used to address the problems of the methods exposed before. These models use parameters of the lithium-ion battery to estimate the SOC using an algorithm, and model-based methods usually use an electrical equivalent circuit model to model the electrical behavior of the battery. The model circuitry is usually configured to simulate the battery chemistries, as it can help predicting battery states, output power, and transient or dynamic behaviors based on the voltage measured between battery terminals. Model-based methods are usually used for SOH estimation also, but in this case they are based on comparing a specific battery model with the real cell performance to adapt it with the SOH. Then, linked to these model-based methods, we have the Kalman filters or standard Kalman filters methods. So, given their self-correcting nature and high accuracy, in recent years, Kalman filters-based algorithms have gained popularity, and we can say that together with the Coulomb counting and OCB methods, it's one of the methods which is more used in the industry. Adaptive filters are usually used to estimate the SOC and SOH as they reduce the influence of noise while improving estimation accuracy and robustness. The Kalman filter, by means of a set mathematical equations, predicts and corrects a new state repeatedly as the system operates. This system compares the measured input data and the output data of the model to calculate the minimum mean squared deviation of the true state. And the main advantage of a Kalman filter is that it can accurately estimate the states affected by external disturbances. And in addition, it does not require a good accuracy of the initial SOC, as it will adapt over time. However, the Kalman filter cannot be used directly for the prediction of the state of a battery, because the state of a battery is a nonlinear system. So it requires an electrical model that has been properly parameterized. So the accuracy of the model will affect also the accuracy of the state estimator based in Kalman filters. Then we have the estimations based in artificial intelligence, where we have the fuzzy logic, the neural networks, Gaussian processes, etc. And all those are computational intelligence methods, and they are focused on the study of adaptive mechanisms that enable the intelligent behavior of complex systems. They have the ability to learn a specific task from experimental data or observation. And this type of algorithm is a common tool for modeling complex systems because of its simplicity in handling big sets of data by mapping the relation between input and output data. For example, neural networks have been used for SOC and SOH estimation because of their nonlinear mapping and self-learning capabilities. In addition, one of its main advantages is that it is not necessary to have information about the internal structure of the battery. And when used for state estimations, voltage, current, and temperature are used as input data, and SOC, SOH, or SOP as output. These kind of methods are gaining popularity in the industry as more and more batteries are being installed, and we have access to a huge databases, so we can use them to implement this kind of algorithms and to have more and more accurate algorithms. Finally, we have, as I said, some novel techniques which are based in novel or non-common sensors. And I think 2 or 3 weeks ago, I assisted to a talk given by Nicolas Quillet from CEA, and he gave us a masterclass about novel and innovative techniques based on these non-common battery sensors, such as heat flux, strain gauge, and ultrasound sensors. As you can see here, all those techniques have their advantages and disadvantages, including the availability of the sensors. But above all, I think that this sensor can be very useful for improved state algorithms, and also to gain knowledge about what is happening inside the battery in the different situations. To sum up, we reviewed very briefly the definitions of battery states and discussed the recent trends in state indicator estimation technologies. In addition, we analyzed 3 new techniques based on novel sensors. And finally, I would like to mention that there is no winner technique, and in my opinion, the best technique is the one that combines different techniques with the objective of having robust predictions, allowing multi-scale estimation, or the possibility to use the same technique with different battery configuration and chemistries. Of course, the one that uses the real field data to enhance the estimation accuracy. And finally, an estimation technique that is also usable for failure diagnosis, guaranteeing the safety of the system. So this was all from my side. I tried to be as brief as possible to have at least 15 minutes coffee break. So thank you all for your time, and see you in some minutes.
Thank you, Inigo. We have some questions. Maybe we can take as defined a very short time for question and answers before our break that is expected to be at 11. The first, they are both reported in the chat. So the first one is related to ESI. The question is, to perform ESI measurements, what is the suggested stimulus current relative to the cell capacity? Does the stimulus current have to be sinusoidal? Sorry. If using a square waveform, do the measurements result remain valid? So it's a very composed question. And then the last part is, does the stimulus current have to be symmetrical with respect to 0, or can it contain an offset? So what about the stimulus and in the ESI measurements? Maybe you can read it.
Yes.
Thank you.
This, as far as I know, I am I am not an expert in this field. Maybe someone can add from the audience in the chat some correct answer. But in my experience, up to now, we only have worked with sinusoidal waveforms, and I think that everyone is working with these waveforms, and I think that the results will be very different if we use yes, if we use, for example, a square waveforms, and also maybe it's not so easy to find the instruments or the equipment to do this waveform. Then about if we can add an offset, yes, we can do it. The stimulus current can be or should be symmetrical, but it can be symmetrical with an offset while we are charging or discharging the battery, or just with the battery stopped without charging or discharging. But of course, we will have different results, and they are used, of course, to obtain different parameters of the battery.
Thank you. Maybe Michael was to add something. I saw him. No. Okay. The other question is a part of to thank for the interesting comprehensive presentation about the sensor location inside the battery. Will it influence the obtained data results? If so, what would be like?
Yeah, this has several implications. So first of all, with respect to the lateral distribution of the sensing spots, this gives you an overview of the temperature distribution inside the battery. So if you remember the infrared camera picture that Inigo has shown in the first presentation, you see that there's not a homogeneous distribution of the temperature inside the battery cell, and you can draw some information out of this temperature distribution, also with respect to the modeling of the battery state. However, I think you did not solely target this lateral distribution, but also the placement of the temperature sensor sheet inside the battery cell. So meaning if it's located below the battery stack, the electrode stack, or inside the electrode stack. So for the moment, we use a closed sheet, and this can be only integrated below the electrode stack. However, we can think of, let's say, perforating this sheet to place it somewhere inside the electrodes, or maybe to integrate it into one of the electrodes, maybe in between the, let's say, to divide the conductive element of the cathode or anode into two foils, yeah, and place the sensor in between. This would also be possible, but this is, let's say, a more elaborate way to integrate this into the battery cell, and this is not in the focus of the project for the moment.
Thank you very much. Maybe there's also an influence on the behavior and the performance of the cell, depending on the position of the sensors. Finally, another question is, which technique is more commonly used in practice for SOX estimation? Okay. Depends on the state.
It depends on the application and in which is the accuracy you need. If we speak the most commonly used, we have a lot of very small applications, all the electronic devices and all these things. And here the most used method is just the voltage measurement, and also the voltage measurement with the Coulomb counting technique. Then in more sophisticated applications, we have the Kalman filter methods. And finally, what we are seeing is that for maybe not so much for SOC estimation, but for SOH estimation, we are seeing a trend to artificial intelligence and to the use of a huge amount of data collected, for example, for different car fleets or bus fleets or all these kind of vehicles. So we can say that the most common one is the OCV plus Coulomb counting, but we are seeing a change in the recent years to the artificial intelligence-based algorithms.
Okay, thank you. The other question is related to ESI again. So why does the EIS curve widen when the number of charge and discharge cycles increases?
Okay, so this is related to the increase of the internal resistance of the battery and also to the decrease of the capacity.
And the last one is on the application that will come most probably. What are the most cost competitive sensor plus model estimations that are currently used in mass produced cells? I think no one. So. If any, maybe.
Yes, I think that nowadays no one is using sensors in mass production cells. And then, of course, in mass produced battery packs or modules, or the most common ones are the so-called normal ones, temperature, current, and voltage sensors.
And so let's hope in the future to tackle these questions. What is the typical frequency range of the EIS test? How the amplitude of sinusoidal waveform affects the internal resistance?
Okay, so it depends on the test that you want to perform and what is the you wanted to analyze. I need to check which are the ones that we are normally using, and I can answer you afterwards in the chat.
Okay, and finally, there's the last one, so then we can take a break. How these measurements can predict in advance an important failure of the system, such as the thermal runaway.
This is one of the objectives of the project. So Alberto, you can ask us in 1 year or 1 year and a half, and we will answer you. Our idea is to find a correlation between the temperature distribution in the cell, or the temperature distribution change and the pressure change with this kind of risky situations. We are going to perform some abusive test with the cells that have these sensors. So we are going to produce a thermal runaway in some cells with sensors, and we are going to measure what we are seeing in these sensors.
Okay, we take just one more because the last one is if we think in the future we'll have mass production. This is one of the output of this project, so we hope. And there is one more. Is there a promising SOC online measurements technique that is not based on SOC reference point? I don't know if Michael or Inigo wants to. Maybe Michael. Now we cannot hear you. You are muted, Michael.
So now I can comment on this mass production issue. So as I already pointed out, the question is about the price of this sensing matrix. And as I pointed out, there will surely, so to my estimation, that so we will not see an instance of this integrated matrices that are based on this vacuum processing technologies. I think these are too expensive. So maybe you can produce them in a cost range at, let's say, below 10 cents per square centimeter. But I think even this is too expensive for integration into battery cells on a large scale. So I think in this application, we will then have the necessity to transfer this to a printing process where we can establish this on a large scale at very low cost. Yeah. But if that's possible, depending on the materials, also the encapsulation can be scaled to these systems, then it will be possible to integrate this in every battery cell.
Yes, then it depends on the number of produced sensors and produced with sensor, and maybe also cost will lower a bit.
Of course, the number of sensors on one sheet is not the cost driver, because if you do the processing on a certain area, it's regardless of the number of elements that you provide by one process, because it's only the cost per area that counts. Yeah? Then it's on the other side also a question of readout capabilities of let's say the data handling capability of the battery management system. What is the, let's say, what is the capabilities of the microcontroller that has to draw some conclusions out of this data, and so on.
Maybe you also answered to the question of Christian about the challenging aspects of mass production. And if you have just a last comment, and then we take the break on the integration of sensor, if it's affected on the design of the cell, on the same format, cell format, like prismatic, cylindrical, so more format of cells. Of course, maybe it will change it.
Of course, it looks much, let's say, much closer to the application if we have a technology where the cell stack is just laying in a plane appearance. Yeah, but there's no. So if you want to integrate it into a cylindrical cell, for example, it must somehow be rolled, yeah? And then it's not so easy to have the sensor rolled with the whole electrode stack, because then it would come back to the problem that I already mentioned in the answer to the first question. Then the sensor must be somewhere inside the stack. And then, as Sylvia commented, you also have to consider what is the effect of the sensor on the functionality of the battery cell. Yeah. So, of course, this is more complicated, but however, there will also be solutions to this question.
So thank you very much. See you. We have this now the break till 11:15, and then the last part, which is more practical, let me say, related to some examples. So let's take me the opportunity to wish to all women in science here, and not only here, a good Women Day, International Day for Women, but also for those that are not here connected. Hoping to get more in SENSIBAT too. So see you in a while. Thank you very much. Be connected.
See you then.
Okay, so welcome back, everyone. So we are going to start the new session on this part on modeling with sensor, and Andrea Marchisio here will present us one practical example. And then immediately after, we have the presentation of Joris van der Hoog about the implementing the models in BMS. Finally, of course, we will have a Q&A session, so please use the chat as before, and then the speakers will be open to answer. So thank you very much, Andrea. The floor is yours. You can share the screen, I think, now.
Okay.
Thank
good
you.
morning. Now I will try to share my screen, I think. Okay. Okay. I think presentation from the start. Okay, I think everything is set up properly. So basically, this is a very brief presentation concerning one practical application, a case study of models applied to the embedding and or implementing sensor inside the lithium-ion cells. Now we will see more in details what it means this practical case. Before to start, I would only present very shortly recap of my institution. So I am from I am Andrea Marchisio from Politecnico di Torino, and more specifically, I work in the research group of Professor Silvia Bodoardo. Currently, I am at the end of at the last year of my PhD. It is basically focused on developing sensor for produce smart li-ion cell, and also there is a section concern models. In this lecture, basically this lecture can be divided in two sections. The first one is more focused on small recap about theory and equation that stay behind the curtains when you use models applied to lithium-ion batteries. The second part from the point that you can see here is will be more focused on the practical example of the case study. Okay. Let's introduce shortly which is this case study. Will be about inserting some kind of interfering elements inside the domain of lithium-ion battery and the possible consequence of that. So maybe some people here in the are already familiar with models, but I would glad to do a small resume about this kind of models. Basically, applied to batteries, to the battery world, you can consider four kind of models. The first one is was already introduced by previous speakers. Are empirical models based on equivalent circuits, so related basically to the electrical laws, and with a combination of discrete and diffused elements, you can model with simple equation like polynomial or linear and exponential equation some kind of the behavior of the cells. Obviously, these kind of models are the most simple one of the four can be applied, are inexpensive by the computational point of view, and are basically generally the more used in the frame of BMS model development, because are very light to be computed. Obviously, the other side of the story is that these models maybe fail in the accuracy to describe phenomena that occurs inside cell during cycling. Going a step ahead in the complexity of the models, we have a single particle model that take into account diffusion of lithium inside solid particles, and where a battery can be roughly modeled with two spheres that represent each one of the electrodes, and separated by an electrolyte. This model, as I already speak, take into account diffusion of and intercalation of lithium inside particles, but doesn't take in consideration concentration gradients inside the liquid phase, namely the electrolyte. P2D model, that is the one we applied in this specific case study, is implement both the features of the single particle models, but introduce also some kind of features that allow to take into account other phenomena. There are both diffusion of solid particles, but also take into account kinetics of extraction, insertion of lithium using a basically Butler-Warner equation, and also difference in concentration in the liquid phase. This model are called P2D because consisted basically in two disparate but connected 1D realms. The first one was concerned porous electrode and the electrochemical reaction that occurs at the interface between electrode and electrolyte. The other realm that account for the second dimension of the model is one-dimensional diffusion based on transport in the particle. These two realms are obviously coupled based on the law of conservation of species. So this model can also extend in more dimension, because as you can see by this picture, the dimensions that are taken into account here are the particles radius and the thickness of the cell. If this model could also extend in measured dimension, taking into account, for example, the section of a cell, or directly the 3D dimension of the cell. For the specific application, we implemented the P2D model in a real 2D realm. Basically, there is a reminder about the measure equation that are used in the model. So electrochemical reaction rates that take place in the interface between solid phase and solution phase are taken into account by Butler-Warner kinetics, both for the electrolyte phase and the electrode phase. In the last part of the slide, there is also an expression that considers exactly the exchange current density. Consider that generally, for the sake of simplicity, this equation is not applied, but the zero current is defined by the user as initial value when you define the C rate in the model. But of course, this equation could also be implemented, and you also can find in some models. The surface over potential is given by the equation that you can see here, and generally is composed by these three terms. So the potential solid surface for the electrodes, basically the potential in the solution, that is the field, and the equilibrium potential of the electrode material. The conduction of electron in the solid phase is generally described simply described by the Ohm law, and take into account the reaction and interfaces and the conductivity of the solid phase. For the electrolyte currents, I describe it according to the concentrated solution theory, was formally developed by Ernst Planck, basically. And you can see in the last part of the slide the equation that accounts for the current in the electrolyte, considering the charge carrying species that are basically ions, obviously. I think we are near the end of this first part of resume. So here I presented the equation that take into account the mass balance in the electrolyte phase and the phenomena that influence this mass balance. As you can see, there are in the extended equation 3 terms: diffusion, migration, and convection. Take into account that the last term, that is convection, in our models and generally in models that are applied to lithium-ion batteries, is neglected because its contribution can be assumed to 0, because the solvent velocity in this kind of batteries and system is not significant. Also, there is the equation for the surface over potential that is similar to the one previously presented in the previous slide. Can be added a term that consider the formation of, say, film, say, growth on the electrodes. Also, in this case, for obviously there are models that are specifically designed to consider say formation, say growth, and are basically applied in the frame of aging studies, but is not the case. So, for example, for the model I will present, the contribution of the last term is neglected in the equation. And finally, the active electrode material is assumed, as already talked, to be made of spherical particles of a defined radius. And as you can see in the equation, there are the condition applied to the equation for the spherical particle. For the specific case study, there is another step that is necessary. Consider that generally these models model the cell like different domains, basically electrodes and a separator on the electrolyte domain that is between the 2 electrodes, with nothing also, okay, could be also implemented other 2 domains that are the current collector, but okay. Consider that in a common situation in general models, there are not any kind of interfering elements inside any domains of the cell. But for example, if you think about to embed something inside the cell, like for example a sensor, or if you consider by the other side a reference electrode, namely a 3rd electrode. So you have to take into account that inserting something inside the domain of the cell can cause maybe problems, maybe generate artifacts, and in a different manner influence the behavior of the cell by the point of view of the cyclability, or induce phenomena on the electrode surface or in the electrolyte, altering, for example, the lithium-ion path between the 2 electrodes during charge discharge cycles. So in the model we applied, the region of where we placed the interfering elements, it is a generic interfering elements. You can think about it like a third electrode, for example, because it is fruitful for the subsequent discussion. So this interfering element is considered to be in solid phase, and in his domain, the electrolyte conservation of mass and charge obviously doesn't occur. So two boundary conduction are applicable for the interfering elements domain. Zero flux and zero current are imposed, like as in the equation you can see here. And if you wrote the equation for the current in the interfering domain, applying the boundary condition mentioned, they drive to the zero current condition on the surface and inside the interfering elements if you apply this boundary condition in the equation you can see here. That is basically the same you already seen previously for the current in the electrolyte domain. Okay, I think I concluded with the first half of the presentation that was more about, as well, recap about equation, fundamentals of models. Now I think a little more funny part. Let's start. By the experimental point of view, we developed the model, and then obviously we perform also some kind of test to validate the outputs of the model. To validate the model, we assembled very well-known coin cell lithium-ion batteries that was assembled following the rules I reported here. So cathode was NMC 622, anode was of graphite. Both material were kindly provided to us by Vard. Cell guard was the separator was a commercial cell guard, a monolayer of polypropylene, and the electrolyte was the common one you can see here. We both assembled cells without interfering elements and also cell with interfering elements that we simulate with a simple patch of Kapton that we inserted here in this position. As you can see, is the yellow circle that could simulate a generic interfering element that is electrically insulated from the surroundings. Consider that this is only a case study, so it doesn't pretend to simulate accurately, for example, a real interfering elements like a reference electrode. For this purpose, we inserted arbitrary dimension interfering element in the cell, and we also drive the model with arbitrary dimension of this element. It was only to demonstrate the employability of this kind of approach to model the embedding of sensor in cell. So it's not extremely accurate and related to, for example, real dimensions of a reference electrode or sensors. By the point of view of geometry, the model was developed based in 2 dimensions. That is, 1 dimension more the classical P2D models was developed originally. There is also an additional feature in this model that to more accurately describe the interfering elements consequence in the cell. We applied a 2D model revolved around a symmetrical axis that are generally considered like 2D axial symmetric models. So you develop the 2D model and revolve it, and at the end you can have a fake 3D model that accounts for the real dimension of the cell, considering also the thickness. Is less expensive by the computational point of view because the program I Yeah, I don't speak about that, but we developed the whole model in COMSOL multiphysics. So the is less expensive by the computational point of view because you consider a 2D model and simply revolve the properties deduced in the surface domain around the axis. If you develop a real 3D model, could be maybe much more expensive by this point of view. So we decided for this approach. There are the features of the model that are listed here, and also obviously model parameters were determined experimentally or provided by literature. It depends by the availability. So what we expect introducing these interfering elements in the electrolyte domain? Well, for example, blocking effect due to physical interference in the ionic flow in the separator, ionic concentration gradients in the electrolyte, especially on the edge of the obstacle, ionic concentration gradients in the solid concentration of lithium inside the electrodes materials. And these features could drive to consequences. For example, charge discharge times reduction and alteration, abnormal surface electrode potential, and induced or error in closed open circuit voltage evaluation if the sensor is effectively a third electrode. And finally, for example, lithium ion concentration peaks and abnormal electrodes utilization and lithiation degree. This maybe could drive also to lithium plating nascent in some regions of the electrodes. Here we report the model and experimental comparison. We simulated one charge and discharge cycle at different C rates. In this slide, I present the results at C/10. We also simulated the behavior at higher C rates, and obviously we validated the outputs of the model with the experimental results made applying cyclability test on the coin cell. So as you can see, in the left panel is the results experimental and model for the non-blocking situation, and to the right for the blocking situation. By this point of view, you can observe an effective reduction on the charge-discharge times in the blocking situation compared to the non-blocking one, due to the interfering effect of the element on the lithium ion flow from electrodes. Here is basically the same thing, but we report the curves at higher C rates, and you can observe the same behavior previously reported. We also run the model at higher C rates, where you can see, as expected, that the interfering features of the interfering elements accounts more and more when you increase the C rate. Unfortunately, it was difficult to assess experimentally this situation because at high C rates, the coin cell used to validate the model didn't perform very well, so we report only the comparison at C/5. But obviously, the model was also run at higher C rates, highlighting a more appreciable effect of the interfering elements. Here we report lithium concentration distribution in the solid phase at different C rates. In this first slide at C/10. This is the concentration of lithium inside the solid domains, namely anode and cathode, at different state of charge, both for the charge and discharge curves. As you can see, this is the situation where the interfering elements, as you can see here, is difficult to maybe can a little difficult to see because in the plots was excluded, but the interfering elements is accounted for this part of the electrolyte domain, and the right part is the undisturbed electrolyte domain. As you can see from initial condition of state of charge 25%, the running on the during charge due to the presence of interfering elements induce abnormal features in lithium distribution inside the solid phase. And here we report the same thing, but in the discharge part of the core, and you can see the behavior is basically similar to the previous one. I think we have a set of slides from now to the other that are basically similar each other, but I will report this plot because you can see that the concentration gradients and abnormal distribution of lithium in solid phase becomes more and more important and evident at increasing C rate. Here we report the results of the model at C/5 C rate in charge, and here the same in discharge. Finally, this is the situation at 1C current. As you can see, the gradients are more exasperated in this situation compared to the previous one. As usual, previously I reported the results in charge, and now in the discharge part of the curve. Here, only for the sake of comparison, I report the situation we plotted if you run the model excluding the interfering elements. Basically, the more simple thing is to set the interfering elements made of to embed the interfering elements in the electrolyte domain properly. And as you can see, concentration gradients and abnormal distribution of lithium are not present in this situation, in this plot. You can see in the last panel that is distribution of a gradient also of concentration of lithium in solid particle inside the anode from the surface to the bulk. This behavior could also be evident in the previous panel with the blocking elements, but the problem is the scale of the problem. The scale of the plot. You can notice the gradient here because the scale is different, but with the interfering elements, they induce an abnormal pattern in lithium distribution, flat the gradients that you can observe here. So are basically present, but flattened by the more prominent features induced by the blocking effect. This is the same as in the previous slides, but for the discharge part of the curve, and you can see a complete recovery of the initial condition of lithium concentration of the cell without the blocking elements. Here we report two small animation that concerns lithium distribution, not in solid phase, but in this situation in liquid phase, so in the electrolyte. Consider that electrolyte is obviously present in the electrolyte domains, that is the one between the two electrodes here and here. Obviously here only in the part that accounts for the undisturbed domain of the electrolyte without interfering elements. And the liquid phase is obviously present also in the porous electrode domains in the void fraction of the material. As you can see, here we report with color gradient the lithium concentration in the liquid phase, and with the black arrows the lithium ion positive ion fluxes in the domains. As you can see, consider one thing, that the dimension of the arrows are proportional to the magnitude of the flux in the cell. So as you can see, in correspondence of the edges of the interfering elements, the flux of the positive ion is exasperated to basically the geometrical interference of the elements in the normal pathway of lithium ions from 2 electrodes. And also, in next slide, I will account for the possible consequences that these features could drive. I think we could make some consideration descending from the plots and the simulation we performed. Electrode particles in the blocked area have a lithium concentration in solid phase that is different from the unblocked surrounding. The interfering elements not only slow lithium ion flux in the electrolyte, but also slow intercalation, and obviously the intercalation of lithium in the porous electrode regions blocked by the solid area of the elements. This concentration gradient in the solid phase could drive errors in electrode potential reading if the interfering element is a reference electrode. Why? We can make another step in this consideration, taking into account that solid phase lithium concentration, the potential you can read using a reference electrode depends basically by the concentration of lithium in the solid phase. It is roughly the set. So if the solid phase lithium concentration relaxes if the cell is set in the rest, the polarization over potential you can observe if you introduce a reference electrode in the cell could decrease and is expected to decrease at longer time. Consider that this overpotential is driven by the abnormal distribution of lithium in solid phase and the discrepancies between the concentration of lithium at surface and in the bulk. Obviously, there's abnormal distribution of concentration are induced by the interfering elements. So this is also a warning when you consider to insert a reference, a third electrode inside the cells, because you can read the potential and assess the potential of single electrodes, but sometimes the fact that you have inserted something in the electrolyte domain can induce self-error in the reading of the potential of the electrode. So maybe your readings can be not completely accurate, especially if you perform a measurement of potential during cell cycling. As you can see here, we performed the last test with the model, and where we simulated the behavior of the lithium concentration in solid phase in the cell during a discharge part of the curve. And then we introduced a rest period. So a rest period where we simulated that we apply a zero current basically to the cell, and in this period the distribution of lithium in solid phase at different times was evaluated. As you can see in the progression of the plots, from the first plot that accounts for the situation of lithium distribution before rest, and the second two that accounts for the situation after rest at different times, you can see in the color relaxation of distribution of lithium in solid phase over time. This what we could expect by this feature that was simulated by the model. So that if you can observe if the potential reading you perform using a third electrode during cell cycling is affected by the same kind of error, this error could approach to zero, so can be neglected if you set the cell rest and evaluate the OCD potential during time. This is a possible explanation of why there's the potential discrepancies between the expected and the observed one approach to the difference approach to zero during time. So we can summarize the results obtained with this model. Interfering element dimension for obviously area and thickness both account for the influence in cell performances, cyclability and capacity, and abnormalization degree. For example, you can find in literature that a common feature to minimize the interference in the potential reading of the third electrode is to reduce the dimension of the electrode. Sure, is true. But a possible alternative solution to avoid this issue and also asymmetry in the electrical feature in the cell could be, for example, to develop a homogeneous thin film, completely non-blocking reference electrode that could be printed directly on cell separator. And this is basically what we are trying to do in the working package 2 of SENSIBAT that is still ongoing. So second point, effect of interfering elements increase with increasing C rates. In the case of a reference electrode, the electrode acts itself like an interfering element, introducing abnormal solid phase lithium distribution, and in turn inducing electrodes potential artifacts. Abnormal and secondary current density, especially at the edges of the interfering elements, can increase lithium plating. Maybe there is a question point because maybe we could evaluate, and the FEM model are useful tool to unravel complex phenomena in the cells. Also, if applied, for example, in this case study to sensor. So this is the end of this short presentation. Thank you for the attention, and I would also acknowledge the very important contribution to not only to this presentation but also to the whole PhD work that I'm currently developing, and so thanks to my colleagues Davide De Santis and Piero Di Prima for their efforts and competence in this field. So thanks for the attention, and yes, I think we conclude with this slide.
Thank you very much, Andrea. I think that questions will arrive immediately after next presentation, which is given by Horace de Hoog or something similar. Sorry for spelling in a wrong way your name.
Nearly there, Silvia.
Nearly.
Yeah.
Of course. So he will speak about implementing the models in the BMS. So please, if you can you share? Okay, perfect. You are sharing.
Yes, it's on the way.
Good. Thank you.
No problem. So good morning. Well, it's nearly midday where I am. So hello everyone. My name is indeed Joris de Hoog. I work as a system engineer, application engineer in Flanders Meek. And I will discuss briefly in a very high level way, let's say, the concept of battery management systems, the design of it, and the operation, let's say. So we'll introduce it. I will introduce Flanders Meek. I'll also introduce the concept of battery management systems. We'll follow this up with a brief discussion on various BMS functions. Also, the architecture and implementation ways are considered. Then, of course, we go to the BMS systems for state estimations, which is quite important, of course. Followed up by a short let's say discussion on sensor integrations, and then we'll discuss some future potential and conclusions. So first of all, Flanders Meek is a Flemish research institute. We are located at 3 centers in the Flemish region. We also include a the Flemish Drone Federation, and we have labs in all 5 Flemish universities. So briefly, these various centers. We have a center in Lommel where we mainly do vehicle development. Then we have the location in Leuven, which is where I'm stationed most of the time, where we do machine development. We have a site in Kortrijk, which is under construction at the moment, which is going to handle mostly the research on customized production lines. And then finally, the Flemish Drone Federation, UCA, is in Sint-Truiden. So we are all over the Flemish sphere, let's say. Of course, we work together with quite some members or companies. We have at the moment we have contact with 165 mainly Belgian and also mainly Flemish companies. And finally, in Flanders Week we are mainly focusing on 4 research topics. Let's say we do smart interconnected products and production systems. We also do customized products at the price of serial production. We do this in an agile, resilient, and people-centric operating, let's say, philosophy. And we also try to remain sustainable in the products and the production systems. And we aim to drive intense collaborative ecosystems and enable profound and integral business transformations for an internationally competitive industry, which is a very fancy way of saying that we try to collaborate with Flemish institutes and Flemish companies to be competitive in Europe. Finally, this is the ecosystem that we work with. So we work with companies. We also have local research partners in Belgium, IMEC among the more, let's say, well-known ones. And also, we, of course, work together with international research partners, which you can see here. For example, Ikerland, Fraunhofer are all represented in this SENSIBAT project. And so we have collaborations with both of them. And then finally, we do pre-competitive research. We also do more applied research, innovation, boosting, and development projects. Contract research, of course, which is an important part of our business, and then research and development projects such as SENSIBAT. Okay, this is enough about Flanders Make. Let's go to the core content of this presentation, of course, which is the battery management systems. So it's important also to note that most of this presentation will be quite high level, because for me it doesn't make sense to go really into the very nitty-gritty of technical stuff. I will mainly present and demonstrate and introduce the core concepts, let's say, of battery management systems. So a battery management system considers primarily 2 topics, let's say. So on the first hand, we have safety, which is related to thermal management, the voltage limits that need to be protected and safeguarded, current limits, some anomaly detection on all the various measurement setups, and then also, of course, the aging of the complete system. This needs to be balanced against the optimal usage of this battery cell, because we want to optimize the let's say the installed charge and discharge capacity. We want to optimize the battery temperature system. We want to enable fast charging and high acceleration modes of an EV, for example. We need to do cell and module balancing, and also consider all of this in relation to the aging of the complete system. So in let's say as a summary, the BMS needs to find an optimal balance between safe operation and performance optimization of the available cell capacity. So how does it work then? So a battery management system reads and stores all of this battery sensor data that has been discussed in previous presentations. It, of course, keeps track of the current and previous states of the battery and all of the modules that are comprising of this battery. it knows what is expected of the battery. So for example, what I mean with this is that it knows how much current is expected by the driveline with regards or with respect to the input of the driver. And also, of course, taking all of this into account, it decides on how the complete system, so the battery and the driveline will operate. As most of you will know, the safest operation of the safest way to handle a lithium-ion battery pack is to store it at, let's say, 50% state of charge at 25 degrees, which means that we are not using it, which is not the goal of anything that is equipped with a battery pack. So we need a balance between this safe operation and the performance of the application. So this means, of course, for example, the acceleration of an electric vehicle, but it could also be the optimization of the operational time of a laptop, the total stored capacity of a solar power battery. So in order to be able to do this, anything that has a battery needs some battery management system. So this BMS, so we have discussed it already briefly. So the functionalities of the BMS include the maintenance of the performance of the pack, the protection of the battery, which is obvious, calculating and keeping track of historical values, and cell balancing. With additional functionalities which pertain mostly to safety-related things that we have discussed already in previous slides. Some of the things that I want to highlight in this on this slide in terms of additional functionalities that might be interesting for you to know is that it is also responsible for example, the disconnection of the battery in the case of an emergency. Let's say that there is a thermal runaway event has been detected, and BMS is responsible for disconnecting the battery from the rest of the system. Also, it communicates data to the operator. In the case of an electric vehicle, for example, this means that the BMS is responsible for displaying stuff like the total available range of the battery pack for an electric vehicle, for example. Also, the time left to charge is another one of these important data points that an operator should know. Another thing that it also is responsible for is the implementation of a limping home mode. Let's say that there is a unexpected contingency or the complete available capacity drops below a certain level or a certain percentage point, that the BMS will be responsible for implementing a mode that is using the least amount of capacity possible per driven kilometer, for example, in order to get the occupant of the electric vehicle to a point where the EV can be charged. This is all achieved by with using two let's say modes. So one of the things that the BMS does is it is responsible for gathering all the general information. So it measures the voltages. So this is the total pack voltage, but also the voltages of the individual modules and the individual cells. It measures currents, as we discussed, and also various temperature points in the complete battery pack, and also the state of the cooling system that has been implemented in the battery pack. Secondly, it uses all this information and more to compute certain parameters. So obviously the various states, but also it decides the max charge and discharge current. It calculates the internal impedance of cells. And as we discussed, it keeps track of charge which is taken or delivered, which is called Coulomb counting. Also, it keeps track of the total energy delivered since the car has been, or the EV has been first used, together with the operating time and the total number of cycles which the battery has performed since birth, let's say. So a quick word on one of these functions, which is a vital one for any battery system with multiple cells. It's called cell balancing, because of the fact, as you are all well aware, that cells are electrochemical devices, these are all slightly different. So all cells have slightly varying capacities, internal resistances, the aging processes are slightly different, meaning that after a while, not all of the cells will be at the same voltage at the same time. So these cells need to be balanced. This can be achieved in two ways. We can do active cell balancing, meaning that there is stuff on the battery cell that is able to transfer charge or capacity between various cells. This theoretically is the most optimal way because it is minimizing losses. Of course, there is also the passive way where cells are discharged to achieve good balance, but of course this is a wasteful way of balancing the cell because this charge is then lost and converted into heat. It's also important to consider that not only cells of a specific module need to be balanced, but that also various modules of a battery pack need to be balanced between each other as well. So how then is this done? So the management of a single cell is relatively easy, right? Because we need to keep track of the nominal operating conditions which we find in the datasheet. So for example, for this 18650 cell, if we look at the dataset, we know that we cannot discharge below 3 volts, we cannot charge above 4.2 volts, and we have defined charge and rapid charge and rapid discharge currents at 1.3 amps, and we know that we can do some pulse discharge current, pulse discharges at 2.6. So these are the let's say the boundaries in which we need to keep our battery, which is relatively easy. However, if we want to extend this system to a battery system which is usable in more specific applications, for example, a battery pack for an electric vehicle, the picture becomes more complicated, right? Because we have a single battery cell, which we just discussed. If we add some cells together in series, we'll get a battery module. And then in order to generate or to develop a battery pack, we need to add various or a couple of these battery modules together, and then having everything together, including the battery housing, the battery management system, some form of cooling, the connections between modules and cells, and the cooling plates consists of our battery system. So we need to, as discussed, keep track of all the individual voltages, but also the voltages of the module, the pack, and the system itself. Same goes, of course, for the currents and temperatures. And so this, you can imagine, increases the complexity of the electrical connections, the communication and synchronization channels, various models that exist of cell, module, and pack. All of this increases in complexity significantly. So let's take a step back and think about various ways of doing this in a practical sense. Generally speaking, a BMS, so battery management system, consists of two elements. The first one is the BMS slave, or the module control unit, which is responsible for all the low-level sensor reading, the organizing of the data transfer to the master, and also doing the low-level real-time safety monitoring. In response to this, there is also, of course, the BMS master, which is a single device which collects all of the available sensor data, performs the high-level analysis of this data, applies battery modules, communicates with other modules or computational devices in an EV, also communicates to the driver, and performs the state tracking. So, for example, calculation of the state of charge, the health, the history of the battery system. There exist also various topologies. So the most simple one is having a centralized BMS where the BMS slave is incorporated into the master, and the decentralized BMS just reads out every cell individually, which is viable for small systems, but not for something like an electric vehicle. Secondly, there exists a distributed system where we have a simple BMS master per cell without a with again like an integrated slave, but this is not a widely used one because you need too much components, and you still have something like an external controller that is responsible for the general operation, right? Thirdly, the modular architecture, which is the most typical layout for a battery pack, where we have a BMS slave module responsible for a specific, let's say, subset of cells or modules. We have these connected to each other and then all controlled by a BMS master. And then finally, we have a decentralized architecture, which is what you see on the bottom right. This has as a positive point that you get the finer control over various modules, with the downside that it is the most expensive version of topology that you can think of. Next, let's discuss the way that the BMS estimates various states. So we'll start with the SOC. State of charge is probably one of the most important things that BMS should keep track of, because it has implications to the total available range, or for example also the time that is still left to charge your cell to a specific point, like for example 100% SOC. We know that there exists a relationship between the cell voltage and the SOC, so one could ask the question, why not just simply measure voltages of the system, for example, the complete battery pack, and then deduce the SOC, which is yeah, a good question, of course. The problem arises when you look at discharge or charge curves like this one. This is a comparison between various discharge curves for 3 different chemistries. So we have an NMC, an LFP, and LTO discharge curve plotted on this slide. And for example, let's say that we have a battery pack consisting of LFP type cells, which is not uncommon. You can see that there exists a very flat region between typically 20% and 80% state of charge, in which the variation of voltage is very small, right? So if we want to simply measure the voltage and then try to estimate the state of charge of this, a small measurement error will lead to a large deviation from the actual state of charge. So that's not good. A secondary problem is if we want to measure the voltage, we need to consider relaxation time. So as you can see here, this is a very simple voltage response to an induced battery discharge current. You can see from the moment that the battery discharge current is applied, the voltage will drop, but it will drop with a specific amount immediately, and then slightly lower while the voltage while the current is still applied. And then once this voltage is once the current is disconnected, or once the current is again settled to 0, you can see that the specific relaxation time is needed in order to get the true voltage of a specific SOC. So that's another problem that we have in direct measurement of cell SOCs, is that we need to leave the battery for a specific amount of time before we can make an actual voltage measurement. So again, another reason why we don't simply measure the state of charge or the voltage of a battery system. So then what can we do? We can, of course, we can apply, as we have discussed in the previous slide, in the previous presentations, we can apply various models. So for example, we can in order to calculate the SOC, we can do Coulomb counting. So I will briefly rediscuss what this is, because I have it on my slide. We know the cell capacity, and we know that the amount of capacity that is exchanged between the battery pack and the outside system. So we can basically keep track of the capacity, and then we can just simply derive the SOC using this information. However, there is of course a big problem with this, is that there is two issues. The first one is the natural drift that will occur due to sensor inaccuracies. And secondly, we have a drift due to the fact that the total capacity is not a static value, but will evolve over time due to aging and internal resistance changes and stuff like this. So what is one of the possible solutions? We can try to, for example, calibrate this system by measuring the total capacity that is available in the system. But this means that we need to completely charge and then discharge the battery system, which is not ideal. What is then the solution that is actually implemented is using a battery model, right? So, for example, in this occasion, we show a battery model that is parameterized by the EIS measurements that have been discussed also before. This gives us relatively good state estimations, especially in the used SOC range. So typically, a battery pack will be used between, let's say, 80% state of charge and 20% state of charge, in order to avoid high and low state of charge regions where either the voltage behavior is not linear, or where we find that the aging is accelerated with respect to what we should see if we just cycle the cell between 80 and 20% state of charge. So that's of course a solution which is implemented, of course, in the cell. A secondary solution is even more, let's say, accurate, where we can, of course, increase the complexity of the models, depending on how much time we have to parameterize the models, and how accurate the estimation needs to be in the end. So one of the examples that was discussed already by Nigo previously is the application of a Kalman filter, which is something that you can see here on the screen. So a Kalman filter, basically what it does is you let the model make a prediction, and then we measure the real voltage response to a specific input. And based on this, we can then use a feedback in order to update the model parameters for the next iteration. So this has as a positive point that we can compensate for wrong initial SOC estimations, but of course this is more complex and more computationally intensive. But it yields extremely good results if applied properly to in a BMS system. Another thing that BMSs need to be aware of is the aging, tracking of the state, the lifetime of a battery system. So as has been discussed, I think yesterday, it is usually said that once a battery system reaches 80% of its initial capacity, then the battery is considered to be end of life. This is especially true for automotive applications. There is some work where the investigation basically is asking the question whether or not this battery can then still be used in less stressful applications. For example, battery packs built from recycled or reused batteries from EVs is something that is of course very interesting. But for automotive applications, generally speaking, 80% initial capacity or 80% state of health is considered the end of life for the battery. This is something that is very difficult to estimate because there exist no direct measurement techniques outside lab environments. Also, as explained yesterday, not all aging mechanisms are completely understood or understood well enough to be able to be modeled in a very accurate manner. Another thing which is difficult with this aging thing is that research data is very hard to collect, right? Because you need to cycle cells for a long time in order to get their aging parameters. And thirdly or lastly, it's very chemistry dependent. So if you develop one model for a specific cell, you cannot apply this model to another cell, because probably even if you compare two NMC cells, the electrochemical composition of these NMC cells will be different enough for these models not to be applicable. So how to solve this? Again, one of the potential solutions is to look at the differential voltage curves. So what is this? This is basically the comparison between the voltage response to a complete cycle, so a complete discharge cycle. You can see this in the figure there. Is that the voltage response or the voltage behavior of a cell changes with respect to the amount of cycles that have been performed by this cell. This seems quite obvious, of course, and this gives us a possibility to develop empirical models based on this. However, in practical sense, this is not very useful, because this again needs, first of all, very sensitive voltage measurements. It doesn't consider the thermal aspects, and as this said, it depends on a full discharge, at least a discharge in the useful range. So this the conclusion that I have on this specific slide is that a lot of research is still to be done in the direct measurement of state of health research domain. Let's call it like this. Lastly, let me just come back to this slide. A lot of research has still to be done. We don't know exactly what is the best way at the moment to directly estimate the state of health for a battery that is used in an electric vehicle. One of the things that we are trying to do in SENSIBAT is to develop models based on this sensor integration inside the cell that will be able to directly infer a, let's say, state of health estimation, right? Finally, the BMS also needs to have an idea of keep track of the thermal behavior. So we need to know the thermal behavior of the cell inside the battery pack, because with this heavily influences the decisions with respect to, for example, cooling strategies, but also avoid the dreaded thermal runaway event that so often catch everyone's attention in the news when an EV catches on fire, for example. Also, the temperature is very much a major influence in the aging. So important thermal events need to be captured and logged in order to keep track of problematic aging phenomena. So all of this to say that a BMS state estimation tracker is quite important on the one hand, but also difficult to implement on the other. The BMS, as said, is responsible for the calculation of state of charge, state of health, but also safety. And these are all influenced by either measurements or models supported by the measurements, which is the main topic or the main feedback that I want to give with this slide. Is the battery management system uses the internal battery parameters, such as the voltages, currents, temperatures, also, for example, which we haven't discussed in this set of slides, but the humidity can also be an important factor for state tracking. And these measurements support the outcome of the models, for example, for the SOC and the SOH. Also, external parameters such as the speed, the vehicle position, environmental conditions, and the vehicle articulation are used for further supporting or data gathering. What is the development that we expect for BMS functionality in the future? Well, it's quite simple actually. Is the BMS functionality depends very much on the understanding of chemical processes, model performances, and computational possibilities. This means that any improvement in those areas will automatically lead to better BMS systems. This is a very generic and general comment that or let's say conclusion that I have on the BMS on the future, but unfortunately there is no magical bullet with which we can solve all of these data estimation problems just by using an improved BMS, whatever that means, right? And to conclude my presentation here, so BMS is so responsible obviously for the battery management, so tracking of states, thermal management, and the auxiliary services that we have discussed. Its operation is based on models and direct measurements. Of course, there exist various architectures, and it benefits greatly from current ongoing research, as we are doing in SENSIBAT, mainly to improve state of health and state of charge estimation techniques. I think that is the end of my slides. Yes, I cannot progress. So if you have any questions, I think we should add them in the chat, right, Sylvia?
Yes, we have already. Thank you very much, first of all, both of you, for these interesting presentations. We have one first question, then I'm sure that something else will arrive. This is more related to BMS. Is the BMS system designed to balance the cells during discharge as well as during charging? From the point of view of electronic circuit implementation, the balancing operation can be carried out by dissipating excess of energy, passive BMS, or by reusing excess energy and you have an active BMS. Do the latter have a real spread? Sorry. This is for Horace.
To be honest, I don't really understand the last question in this text, but it is my opinion that most of the cell balancing will happen during charging, right? Because that's the most optimal moment to do this charge distribution. But of course, this is something that in practice is very difficult to figure out what exactly is going on in the sense of how battery integrators or vehicle manufacturers are doing this specifically, because yeah, the BMS is one of these trade secrets, right? So it's possible that somebody one specific manufacturer is doing the cell balancing mostly during charging. One of somebody else is doing it mostly during discharging. It's something that that is an important, let's say, trade mark secret.
Thank you. Maybe it also will depend on the number of sensors and how many functions we need to evaluate. There's a question for Andrea, very fast. Which software do you use for modeling?
Okay, yes, it's console multiphysics or one of older versions.
Thank you. And the other one is, thank you for your talk. I think I missed it, but I want to, what is the difference between decentralized and distributed BMS? Is it just the external control or are the individual BMS different? And then there's also a question on slide 24, what is causing the immediate drop of voltage prior the relaxation? So, okay, but maybe firstly, the question about the decentralized and distributed BMS.
Yes, so the main, as you can see here, the main difference is that there is indeed a controller on the distributed system where this basically, I mean, the difference between this and the modular architecture is slightly fuzzy. The same goes with decentralized architectures. The controller in the case of a distributed system will safeguard the or let's say will be responsible for the communication between the various simple cell BMSs that you can see here, while the decentralized architecture relies mostly on communication between BMS systems individually. So let's say you can consider this to be a question of attitude from the various BMS systems. Is the communication from the BMS units organized from the BMS unit itself? Then you can talk about the decentralized architecture. If the BMS, the BMSs or the BMS masters in this case communicate due to the fact that they are managed managed from a controller standpoint, then you have to talk about the distributed system. But of course, the difference is not that important, I think. With regards to the second question, so what is causing the immediate drop of the voltage prior to relaxation? So this is maybe a question that my colleague Andrea is more apt to or more capable of answering. But the main let's say feedback that I can give is that there is different internal resistances that play a part in the voltage behavior when a battery current or when a current is applied, right? Andrea, do you have a comment on this?
Yeah, yes, it's basically the same profile you observe if you perform some kind of interlock current test. It is basically an ER drop, the first step you can observe in the curve you are presenting here, basically due to this event. Then the subsequent curve is due to basically relaxation of that occurs inside the solid phase of the cell, so basically electrodes. So as you can, as you already say, the first one is more related to an electrical point of view. That is ER drop, more ohmic. The second one is more related to relaxation and redistribution of species concentration inside the active electrodes.
It's really ohmic drop, the first part. It's related to the change of current, of course, as V is R multiplied by I. So I fully agree with Andrea. There's still another question that is, can you provide an order of magnitude of computational power required to a MCU in order to perform all the BMS tasks?
So there is two aspects to consider, or maybe I can just give a small overview of the solution that we are going to develop for the SENSIBAT project. So the MCU, or let's the module control unit, so the low-level slave functionalities within the SENSIBAT project are going to be handled by a Arduino Due. So this is low-level, low-power microcontroller, right? The BMS master in our case is going to be running on a Arduino, on a Raspberry Pi. So this is the kind of computational power that you would need in order to keep track of simple stuff like, and also keep track of a simple, I mean, I want to say, wait, let me rephrase. So we use a Arduino Due, an Arduino Due for the BMS slave operations, and we use a Raspberry Pi for the BMS master operations, which is more than enough to keep track of all of this information. Of course, in a commercial battery management system, you will not find these specific development boards, but most probably the computational power will be in the order of magnitude that is present in both of these systems.
Thank you. There's still another question. So what could be the appropriate sampling frequency for the parameters being measured?
Yes, that's a good question. And I think this is, again, a question of finding a good balance between sampling frequency and the things that you want to achieve. So, for example, if we use the sensor integration for model verification, yeah, then it depends on the amount of or the amount of accuracy that you actually need. So you need to be pragmatic, right? In the battery management system for a vehicle, you don't need a sub-percent accuracy of your state of charge, because the complete battery capacity is so big that that it doesn't really matter. So there you don't have to sample every. I mean, you don't have to sample at the 20 hertz frequency, for example. Probably a 1 hertz frequency will be sufficient. But again, you will not find this information from battery BMS manufacturers, because this again is something that is appropriate or that is a closely held secret. In our case, this is something that we are going to develop, and that also something that we are going to investigate is the optimal sampling frequency. So difficult to say also.
Okay, thank you. So I think there is no additional question, or okay, yes, there's a thumb up. So if no additional questions are coming, let me thanks, of course, the last speaker, Joris and Andrea, but also all the speakers of yesterday and today. Of course, Ross for setting all of these practically. So thank you very much. Thank you to Inigo, the coordinator of SENSIBAT project. And so thank you to the European Commission for funding SENSIBAT. I think it's a very good community, strongly working, going straight in the direction. So let me also thank Battery 2030, of course, Jürgen Garke, for the very big work, keeping us all in the same direction and pushing us to prepare all these, I think, very valuable seminar and zeroing course. I hope you enjoyed, and keep posted, and keep in touch. I don't know if Inigo, you want to add something as coordinator of SENSIBAT, just a greeting.
No, I think that you did it very well, and thank you everyone for being with us these 2 days. And we keep in touch via our website with our latest results, and I hope to see you soon.
I think that the registration of those days will be posted, will be uploaded on maybe on YouTube, and then a link through SENSIBAT webpage will be available. Is it? Can we?
Yes,
Okay.
that's correct. I will
Thank you, Ross.
create a recording, and also the presentations will be put online, and then I will share them with everyone who registered for the event. So maybe it will be today or tomorrow. Yeah.
Yes. Just thank you very much, and see you soon. Bye-bye.
Bye.
Bye. Thanks.
Thank you.